Hi, this is Grover with Blue Collar Codes, Quick and Dirty, episode 22. Going to go over data structures. Going to touch upon how memory works, then the low-level array, and then how Python lists are implemented. If you wish to follow along, episode 22.py, link in the video summary. So to start off, why are data structures in general important? It's simply because of things called time complexity and space complexity, which you can boil it down to efficiency in how fast the data can be processed, and then efficiency in how much memory the object or data construct requires in order to exist for the actions to be performed on it. And so that's why data structures are important, in that different types of data and different types of algorithms require different data structures in order to meet their potential as far as space complexity and or time complexity. And so to dive into what memory is, memory plays a large part as to how fast something can run and how efficient it can be based on what these abstractions require in memory and memory usage. So in layman's terms, memory, I would just think of it as locations on your computer that can house a maximum amount of information or data, and they can each be accessed by something called a memory address, which is in O1 time. And just understand that different objects in memory require different amounts of these minimum sized locations in order to be implemented. So main takeaway again is different things take up different amounts of memory. Now to dive into the low-level array and how memory plays a part, is a low-level array is one, especially when you're talking about the compact array anyway, it is one that requires a single continuous or contiguous block in memory, and all of the values within them need to be homogeneous so that the size can be predetermined, sought after by the system, and blocked off for this data. So homogeneous basically means just they all have to have the same size. And in this terms, because Python and other languages are outlining size of elements by their type, that just means they all have to be the same type, for the most part. And so to make a compact array then, you need to have all items of the same type. It'll block off a location in memory, and then it is fixed. And the location in memory has to be, say, memory address from 100 to 150. So they're very memory efficient, and they definitely allow for fast access of the data. But the one thing to remember as well is that they are finite, they are fixed, they're immutable. It's not something where you're going to be resizing it based on adding values, inserting or removing values. So that's where the efficiency comes in, is that it's all of the data or values are, in proximity of one another, so the close proximity helps, and then they're all continuous. So the other low-level array can be considered a referential array, or is called a referential array, and it's basically just a overarching construct that is creating an array of pointers to other objects. And this can be resized, meaning you're adding and removing elements to it. However, what that means is that initially the array is going to be implemented and choose a default size. Say it needs to have 10 slots, or it has 10 index locations, and then when you add that 10th one in, it's going to be going through a resizing system process, and basically it's going to say, okay, we've gone beyond the 10 indexes that were available in this list as far as capacity, and so on the back end, unbeknownst to us, the user, it is going to search for a larger continuous chunk in memory, and then it is going to have to copy all of the old values into that new location and then reallocate or free up that old location in memory so that it can be used for other things. And this is I'm talking just about the array of references, not the actual objects themselves, because these can be stored dynamically in other areas, so based on their size. So they don't have to be stored with the overarching list abstraction here. So that's a referential array, and the key takeaways here are that it is just an array of references. It's not in proximity or direct proximity of the data points here, such as John Jacob. These can be stored in different locations of memory. And the other thing to go over one more time is just that the initial capacity of this referential array, the array of pointers here, L, may be a certain arbitrary number, not arbitrary, it's chosen and set, and you can read about that in this Python area about memory. But when the capacity needs to change, there is a cost to that because it needs to find a larger chunk of memory that's continuous for this array of pointers, and then it's going to have to copy that information over, then reallocate the old space. And so that's very similar to how the Python list works in itself. It is a dynamic array that can be resized as needed, but it doesn't have to house, say, homogeneous elements or values. It is something that can house other lists, and it can have a bunch of different data within it. And that data is stored in different locations than the actual list of references. So when is an array efficient? So an array is efficient when the data is static and doesn't need to frequently change in size, because ultimately if you are going to be housing a lot of data points here and it's constantly going to be changing in size, then instead of getting, anytime you're making an append before you hit capacity, meaning if I'm adding David or what have you, and then another name, these additions called, for the Python list it's an append, just adding to the end of the list is done in O1 time, except for when you reach the end, the maximum capacity, then it's going to go be ON because it has to copy all of those other values. So if you have data that's constantly changing, like you're adding 1,000, you're removing 1,000, adding 1,000, removing 1,000, say, system processes or what have you, that's when it's not efficient. But if you have information that's relatively static, needs to just be maintained, then it's probably the most efficient when you have an array, simply because of all its proximity to itself and its ability to be cached. So it's inefficient when you have a dynamic and rapidly changing data set. So the last element I'm going to touch upon is basically just if you wanted to see the actual size of your objects in Python, they have a module called system, and the method is sys.getsizeof, and you can get the actual size in bytes of these constructs. Now just make note that if you are going to use that getSize method on, say, this list, this referential array, it's only going to give you the size of the referential array of pointers. It's not going to go dive deeper or recursively and find and calculate and summate all of these different objects. So again, this was Grover with Blue Collar Codes. Thanks for joining.